In section 8, we're going to be looking at something called systems of linear equations in two variables. Section 8 and section 9 are going to be sort of a tandem set of sections because we're going to be looking at the same concept of system of linear equations. In section 9, we're going to be looking at this in 3 variable and not just 2. So it's important that we get the fundamentals here in section 8 for how to work with 2 variables and 2 equations, and then we'll just extend that into the 3-dimensional sense, which will be the 3 equation and 3 variable world. So let's start with some definitions, because there's some language that I want to be sure that we're all using correctly and the same, so that way this conversation will go smoothly. A system of equations, definition 8.1 says a system of equations is a set of equations, specifically a set of equations that involve the same variables. So it's interesting because we're familiar with the concept of a set. We've seen things like, let me show you an example down here, 1, 2, 3, 4, and I'll put comma, ... And that's an example of a set of numbers, and this specifically would be equivalent to the set of natural numbers. We've also seen things that are sets of ordered pairs, such as maybe 1, 1, 2, 2, 3, 3, and then I could say that that set of ordered pairs would continue in that way. And this would be an example of a function or a mapping. A mapping and a function, those are a set of ordered pair. And so now we're talking about a set of equations. So a set of equations is known as a system of equations. So you might see something, let's say like this: y equals 2x plus 3, comma, y equals 3/4 x minus 7. And that would be a set of equations. Now I will say this, when we're talking about sets of equations, we typically don't list them horizontally like this, but instead we do it this way. We will make a larger curly brace for the left side, and then we'll list the equations vertically, and then we don't have to separate them with a comma when we do it like this. And another part of the convention is that you don't put a ending curly brace on the right. This is all you need to represent a system of equations. And if there's 3, then you just list all 3 of them vertically, however many number of equations you may have. Now what we're going to be specifically looking at is statement number 2, a system of linear equations. So the only way that a system is considered a system of linear equations is if each equation is itself linear. So the example that I drew, that I wrote out here, is an example of a linear system of equations because each one of the equations is linear. So that's one set of vocabulary, the idea of system. The next thing that I want to get across to you is the idea of solution. So we're first going to define in 8.2 solution of a system. A solution of a system is an assignment of values for the variables. Now you can make lots of assignments for the variables, but only the ones that make each equation in the system true are going to be accepted as being solutions. Now this concept actually is not foreign to us. For example, if I say 4x is equal to 2, and I say solve 4x is equal to 2, then that means that you're trying to find an assignment for the variable that would make the statement true. So if we were to let x be equal to 1/2, then I would have 4 times 1/2 is equal to 2, which means 2 is equal to true, and that's a true statement. And so that would mean that 1/2 is a solution to that particular equation. Now what we're getting at is an entire system, not just one single equation, but a system which has multiple equations in it. So each equation, let me qualify this, each equation in the system has to then be true. So it's a little stricter requirement, but we'll be sure to do some examples on that in this section. And then the last statement here in definition 8.2 says to solve a system means find all solutions of the system. And I'm going to emphasize the word all here. You have to be sure to find all of the solutions. Now with the example that I showed here with just the single equation, there is only one single solution there. However, there are certainly equations out there that can have multiple solutions. For example, if I was to say solve x squared equals 9. If I let x be equal to 3, then I would get 3 squared equals 9, which means 9 equals 9. That's a true statement. And if I was to let x equal -3, then I would have -3 squared is supposed to equal 9, which also gets me a true statement that 9 equals 9. So then I can find two different values that both make the statement true. So then my solution set would be both -3 and +3. So that's, when I say to solve something, that means you have to find all of the solutions. Now it's also conceivable that there could be no solution. For example, again, we're just using single equations here to help illustrate the idea, but we're going to eventually get into the system stuff on our examples. But if I was to say solve the square root of x is equal to -4. So you might try some things like, I don't know, let x equal 16. So then you'd have the square root of 16 is supposed to equal -4, but the square root of 16 is +4, and the last I checked, +4 is not the same as -4. That's a false statement. Okay, so maybe you make an adjustment. What if you were to try the, let's let x equal -16. That's the issue, is we just didn't have the negative there. So if we do that, then we would have the square root of -16 needs to equal -4. Oh, but wait, the square root of a negative is non-real. And if something's not real, is it going to make sense to say that it's equal to a real number? That doesn't make any sense. So that's also false. And there would be no way for us to be able to find a real value that would end up solving this particular equation. And so when that occurs, we can say that the solution set is empty. It's an empty set, or we can use the empty set symbol for no solution. So we can have a variety of things occur whenever we start talking about equations, and we can also have that same concept translate over into solving a system.